Hi, this is the Renegade Mathematician here. Thanks for joining me again. And today we're going to keep discussing cofactors and minors. Last time we showed an example, or really it's kind of a common result that's, I think, straight from the book, that if you have a triangular matrix, be it upper or lower triangular, that the determinant is just the product of the entries along the main diagonal. And today we're going to do we're going to calculate a determinant using both the method of cofactors and also by messing with the determinant until we get it to be triangular so that we can just multiply the entries along the main diagonal. So you can see both, I guess, ways of skinning the cat. Alright, so for example, we're going to consider the determinant with entries 1, 2, 3, 4, 5, 6, 7, 8, and 9. You can see I'm very imaginative, but this determinant actually turns out to be kind of convenient. So the determinant there is equal to this when you, or by the cofactor expansion theorem. And notice we got the, we're expanding about the first row. So the entries in that row are 1, 2, and 3. So the first term in the sum is 1, okay, times the cofactor that you get from deleting the first row in the first column, plus 2 times the cofactor that you get from deleting the first row, second column, plus 3 times the cofactor that you get from deleting the first row and the third column. That's just by the cofactor expansion theorem. But that is equal to this, right? I'm actually just calculating those determinants by using the shortcut for 2 by 2 determinants. And so I get the 45 minus 48 from this term. I get the negative 2 times 36 minus 42 times this one, or from that term. And I get the 3 times 32 minus 35 from that term. Okay. Now if you just do the arithmetic, what you end up with is negative 3 plus 12 minus 9, which comes out to 0. Okay. So doing it the other way now. Now by adding negative 4 times row 1 to row 2, we get this determinant here. Where what I've done is I've looked at the second row and I said there's a 4 there. It's not upper triangular unless I can get a 0 there. So I have multiplied the first row by negative 4 so that when I add it to the second row there will be a 0 there in the second row. Okay? And remember, a previous result told us that we can add a multiple of one row to another row without changing the determinant. So that's how we can get away with doing this. Okay? And now, by adding negative 7 times row 1 to row 3, we can obtain this, right? So we're targeting that 7 in the third row and saying, I'd rather that was 0. And so we just multiply the first row by negative 7 and add it to row 3, and we get a 0 there. Okay? Now, what do you suppose we're going to focus on next? Now, the only thing standing in the way here at this point, standing in the way of us having a triangular matrix, is there's a negative 6 there in the third row, second column. We'd like that to go away. So what should I do? I don't think I'm going to add a multiple of the first row because that would mess up the 0 that we have in the first column. I think what I'll do is I'll multiply the second row times negative 2 and then add it to the third row. Okay. And we'll get this by adding negative 2 times row 2 to row 3. Now, notice that had an unintended consequence of putting a 0 in the third row, third column. Doesn't matter. So long as the entries below the main diagonal are zeros, doesn't matter if there is an entry on the diagonal that's 0. Don't care. In fact, that makes it super easy. Because, okay, since a sub ij is equal to 0 for I greater than j, then we now have the determinant of an upper triangular matrix. Hence, we may take the product of the entries along the main diagonal to obtain. It's super easy. It's going to be 0 because 1 times negative 3 times 0 is 0. Derp. Notice we got the same answer both ways. They both work. You just get to choose which way you'd like to do it better. If you're good at your algebra and you like doing row operations, cool. Do it that way. Otherwise, use the method of cofactors. They both work great. And that's it for this video. Thanks for joining me. See you next time.